Good evening, and welcome to The Sleepy Scientist. This channel is a gentle corner of the universe where you can let go of the day, close your eyes, and drift into sleep while listening to calm stories of science. Tonight we're turning to one of the deepest mysteries in all of physics. What is space-time? It sounds simple, but hidden within that single word lies a story that stretches from ancient philosophers to modern telescopes, from the smallest particles to the largest galaxies. Before we begin, I'd love to know, where in the world are you listening from tonight? It's always fascinating to see how far and wide these stories travel, and if you find these videos help you to relax or spark a little curiosity before sleep, I'd be grateful if you could give the video a like and subscribe to the channel. If you're already subscribed, thank you so much for your support, and if you haven't yet, please do click the notification bell so you don't miss the next journey we take together. I like to think of these videos as both lullabies and lessons, though I hope this one isn't so interesting that it keeps you awake. But if it does, at least you'll drift off having learned a little about the fabric of reality itself. So then, what is space-time really? Is it a stage where events unfold, or is it part of the cast itself? Let's step quietly into that mystery. Space-time is not something we can touch or hold in our hands, yet it defines everything we experience. Every heartbeat, every sunrise, every galaxy wheeling across the sky takes place within it. And yet the nature of space-time is far from obvious. To ancient thinkers, space and time were separate and absolute. To Newton, they were an infinite backdrop against which the cosmos moved. To Einstein, they became fused, dynamic and alive. In this video, we'll trace the journey of that idea, how it arose, how it reshaped physics, and how it continues to challenge us. We'll explore the relativity of time, the bending of light around stars, the strange ripples of gravitational waves, and the puzzles of black holes. We'll look at attempts to stitch together space-time with the quantum world, and even ask whether space-time itself might one day prove to be an illusion. Along the way, we'll pause for thought, philosophical reflections on whether time truly flows, or whether past and future exist all at once. We'll look at practical ways space-time shapes our lives, from GPS satellites to the way astronauts experience time differently in orbit, and we'll wander into the speculative edges, wormholes, closed time loops, and the strange shapes space-time might take beyond what we can observe. This is not just a journey through physics, but through imagination and wonder. By the end, you may not find a final answer to what space-time is. No one has one yet, but you will have walked its contours, from the human scale of minutes and meters to the cosmic scale of billions of years and trillions of kilometers. So, settle in, let your mind drift gently, and prepare to explore a question as old as thought itself and as fresh as the latest discovery. What is space-time? Long before physicists spoke of space-time, people were already wrestling with what space and time actually were. To us they feel obvious. Space is the room around us, and time is the steady ticking that carries us from morning to night. But if you ask what space really is, or whether time flows like a river, or simply marks change, the answers become slippery. Ancient thinkers sensed this strangeness and began shaping ideas that would echo all the way to modern physics. In ancient Greece, philosophers argued about the very existence of empty space. Aristotle, the great system builder, believed in a universe where everything had its natural place. He rejected the idea of a void. To him, space was not some invisible container, but rather the ordering of positions of bodies. Remove all the bodies, and there would be nothing left, not even a space in which they once were. Space was relational, defined only by the positions of things. Not everyone agreed. Democritus, centuries earlier, had imagined a universe made of tiny indivisible atoms moving in a vast, infinite void. For him, the void was absolutely real, a kind of stage upon which atoms danced. Without it, their motion would be impossible. The void was emptiness, yes, but emptiness with structure and significance. This disagreement, whether space exists in its own right, or is just the relation between things, would resurface again and again in the history of science. Time too was puzzling to the ancients. Aristotle viewed time as a measure of change. Without motion, without events, there could be no time. A world frozen in place would also be frozen in time. Yet other philosophers wondered whether time had its own existence, a kind of invisible backdrop against which everything moved. These early musings might sound abstract, but they frame the questions physicists still grapple with today. Centuries later, Isaac Newton gave space and time their most influential form before Einstein. For Newton, space was absolute, infinite, and unchanging. It was a vast container that existed whether or not anything filled it. Time too was absolute, flowing evenly everywhere in the universe like a cosmic metronome. The apple fell from the tree not only because of gravity, but within a perfectly still framework of space, ticking forward in perfect time. Newton's picture was clear, simple, and powerful. It allowed him to describe planetary motion with stunning accuracy. The Earth's orbit around the Sun could be traced with mathematical precision, because both were moving through the same fixed, eternal stage of space and time. If you were to empty the universe of stars and planets, Newton insisted, space and time would still remain, stretching on endlessly. Not everyone accepted this. The philosopher Gottfried Wilhelm Leibniz argued that Newton's absolute space and time were unnecessary. To Leibniz, all that mattered were the relations between things. If there were two identical universes, one shifted slightly to the left and nothing else distinguished them, how could they be different universes? Space, he said, was simply the network of relations between objects, not a real substance. Time was the sequence of events, not an independent flow. This debate between Newton's absolutes and Leibniz's relations was not just philosophy. It shaped how people thought about the very fabric of reality. If space and time were real entities, then they could exist without matter. If they were only relational, then they had no independent existence at all. For centuries, the argument continued without resolution, echoing through the halls of science and philosophy alike. By the 19th century, physics had grown more precise, and new phenomena demanded fresh ideas. Electricity, magnetism, and light hinted that space might not be entirely empty after all. Scientists spoke of an invisible medium called the ether, a kind of substance filling the cosmos through which light waves rippled. It seemed like Newton's absolute space given physical form. Yet experiments searching for this ether came up empty, shaking confidence in the old picture. And so, by the time Albert Einstein appeared on the scene, the stage was perfectly set. The ancient questions of Aristotle and Democritus, the clash between Newton and Leibniz, the rise and fall of the ether, all had chipped away at simple notions of space and time. What seemed obvious had become uncertain. Were space and time real, or just convenient concepts? Were they absolute or relational, stable or flexible? These unanswered questions hung in the air as physics approached the 20th century. It was in that climate of uncertainty that Einstein introduced a new vision, one that did not simply take sides in the ancient debate, but dissolved the old categories entirely. Space and time were not separate at all, but two aspects of a single entity. The answers of the ancients and the absolutes of Newton would fade into history, replaced by something stranger and far more beautiful. In hindsight, the journey seems inevitable, as though the universe had been nudging human thought step by step toward the idea of space-time. But for those early philosophers, and for Newton and Leibniz after them, the puzzle of what space and time truly were was as mysterious as ever. Their debates remind us that even the most familiar aspects of existence can turn slippery when examined closely. What feels obvious in daily life, the room around us, the passing of hours, is in fact among the deepest mysteries science has ever faced. The year was 1905, and a young patent clerk in Bern, Switzerland, was about to change the way we think about reality itself. Albert Einstein was working long hours reviewing technical patents. Yet in his spare time he wrestled with problems in physics that had stumped the best minds of the era. One puzzle in particular kept bothering him: the speed of light. At the end of the 19th century, experiments by Albert Michelson and Edward Morley had tried to detect the motion of the Earth through the so-called ether, the medium that physicists believed carried light waves. To everyone's surprise, the experiments found no difference in the speed of light regardless of how the Earth was moving. Light seemed stubbornly constant, unchanging, indifferent to whether you were racing toward it or away from it. This result didn't fit with Newton's mechanics, where velocities always add up. If you're running on a moving train, your speed is the train's speed plus your own. Shouldn't light behave the same way? Einstein decided to take a radical approach. Instead of clinging to the old assumptions, he accepted the strange result of the Michelson-Morley experiment as a fact of nature. Light, he proposed, always travels at the same speed, about 300,000 kilometers per second, no matter who measures it or how they are moving. To preserve this rule, something else would have to give way, and that something was space and time themselves. From this bold idea, special relativity was born. If the speed of light is fixed, then time cannot tick the same for everyone. Imagine two observers, one standing still on the ground and another zipping past in a spaceship. Each sends out a beam of light and measures its speed. Both, according to Einstein, must record the same value, no matter their relative motion. To make that possible, time itself must stretch or compress depending on how fast you move. This leads to the phenomenon known as time dilation. A moving clock ticks more slowly than a stationary one. To the person carrying the clock, everything seems normal, but to someone watching from the outside, the moving clock runs at a gentler pace. This isn't just a thought experiment. We have tested it countless times with atomic clocks on airplanes, satellites in orbit, and particles racing around accelerators. Time genuinely flows differently depending on your motion. Length contraction is the twin effect. If time is altered, space must be too. An object moving at high speed appears shortened along the direction of motion. To the person inside the spaceship, it feels its normal length. But to someone watching it whiz by, the craft is squashed, compressed by the mathematics of relativity. Again, this is not an optical illusion, but a fundamental feature of the universe. Space and time are flexible, bending themselves to preserve the constancy of light. Perhaps the strangest idea to emerge from Einstein's work was the relativity of simultaneity. In everyday life, we assume that two events happening at the same time for one person must also happen at the same time for everyone else. Einstein showed that this is not true. Imagine two lightning bolts striking both ends of a moving train. To someone standing on the ground, the strikes might appear simultaneous, but to a passenger riding the train, moving toward one bolt and away from the other, they would not. What counts as now depends on your state of motion. The present moment is not absolute but relative. These ideas were shocking. They forced physicists to abandon the comforting notion of a universal time ticking in the background. Instead, each observer carries their own time with them, woven together with their own space. The faster you move, the more your personal version of space and time diverges from someone else's. The old absolutes of Newton were gone, replaced by a strange new order where the universe adjusts itself so that light's speed remains unbroken. Special relativity also produced the most famous equation in physics, E equals mc squared. Energy and mass, long thought separate, are revealed as two sides of the same coin. A small amount of mass can unleash a tremendous amount of energy, which later became the foundation of nuclear power and the terrible destructive force of atomic weapons. Yet the equation is not only about power, it captures a deep unity in nature, showing that matter itself is a condensed form of energy, tied into the structure of space-time. Einstein's 1905 papers caused a quiet revolution. They were not accompanied by fireworks or instant recognition, but their consequences began to ripple through the scientific community. Here was a world in which the stage of reality, space and time, was no longer rigid but elastic. The constancy of light demanded it, and once accepted, the whole universe looked different. Although strange, relativity fits the evidence beautifully. Muons created in Earth's upper atmosphere should decay before they ever reach the ground. But thanks to time dilation, from their perspective, their internal clocks tick slowly enough that they survive the trip to detectors below. Satellites guiding our GPS systems run on clocks that drift from those on Earth because of their speed and altitude. Without correcting for relativity, your phone would place you kilometers away from your true position. These are everyday reminders that the oddities of Einstein's theory are woven into the fabric of our modern lives. At its heart, special relativity planted the seed of a new way of thinking. Space and time were not separate entities at all, but two aspects of a single reality. It was not yet fully called Spacetime. That step came a few years later when Hermann Minkowski gave the idea a mathematical home, but the foundations were set. The world would never again be viewed through the lens of absolute space and absolute time. Instead, reality became a tapestry where motion, measurement, and even the definition of now were all relative, bound together by the unshakable speed of light. Einstein, the young patent clerk, had dared to ask, what if the rules we thought were obvious were simply not true? His answer reshaped physics forever, leaving behind a universe far stranger and far more beautiful than anyone had expected. In 1908, just 3 years after Einstein's remarkable papers on special relativity, a mathematician named Hermann Minkowski stood before an audience in Cologne and declared that physics had entered a new world. Einstein's strange new ideas about time and space bending to keep the speed of light constant were difficult for many to grasp. They were equations on paper, powerful but puzzling. Minkowski offered a vision that reframed them in a way both beautiful and profound. He announced that space and time were not separate at all, but part of a single, unified, four-dimensional fabric he called Spacetime. Minkowski had once been one of Einstein's teachers, though Einstein had not been the most attentive student. Legend has it that Einstein thought of mathematics as too abstract for the kind of physics he wanted to do. Minkowski, however, saw at once that Einstein's relativity cried out for a mathematical structure bigger than anything Newton would have recognized. When he fused 3 dimensions of space with one of the time, the oddities of relativity suddenly became natural. To picture this, think of an ordinary graph. One axis marks distance, another marks height. You can plot a line showing how an object moves across a plane. Now imagine adding a third axis for depth, and you have a 3-dimensional space. Minkowski's leap was to add a 4th axis for time. Each object in the universe does not merely occupy a point in space, but traces a path through space-time, a continuous line called its world line. A world line is the history of an object. Your world line begins with your birth, stretches through each moment of your life, and would continue to the very end. A rock sitting on the ground has a world line too, though it is a vertical line in the diagram, marking the steady march of time while its position in space remains constant. A spaceship streaking through the cosmos draws a tilted world line, cutting across the fabric of space-time at an angle. Every event in the universe, from the blink of an eye to the collision of galaxies, can be plotted somewhere in this 4-dimensional map. One of Minkowski's most striking contributions was the concept of the light cone. Imagine you switch on a flashlight at a single moment. The light spreads outward in all directions at the speed of light. In space-time, that spreading forms a cone, one extending into the future where the light will reach, and one stretching into the past, marking all the places from which light could have reached you. Events inside the cone are those you can influence or be influenced by. Events outside it lie forever beyond reach, no matter how fast you travel. The light cone shows the ultimate limits of cause and effect in the universe. Space-time diagrams, with their axes of time and space, their world lines and light cones, became the visual language of relativity. They show in a glance what is hard to express in words: how simultaneity is relative, how signals move, how no object can ever cross the boundary of its light cone faster than light itself. For many students and physicists, the diagram is the aha moment when Einstein's abstract equations click into place. It was in that Cologne lecture that Minkowski delivered his famous line, "From henceforth space by itself and time by itself are doomed to fade away into mere shadows, and only a kind of union of the two will preserve an independent reality." It was a bold pronouncement, but it captured the spirit of the age. No longer could one talk about where without also talking about when. Every location had a time coordinate, every moment a spatial one. The world was not a sequence of separate instants played out on a stage of empty space, but a single four-dimensional structure in which events were woven together. The idea was initially so radical that even Einstein himself hesitated. At first, he considered Minkowski's mathematics unnecessarily elaborate, but as he delved deeper into gravity and the problem of accelerating frames, he realized that Minkowski's spacetime was not an optional tool, but the very key to progress. Without it, the path to general relativity would have been far harder. Minkowski's vision also altered how people thought about the nature of reality itself. If an event in the future already exists as a point in the spacetime diagram, does that mean the future is already there, waiting for us to arrive? This picture lends itself to the so-called block universe, where past, present, and future all coexist in a four-dimensional whole. Our experience of time flowing may simply be the way consciousness slices through the block, moment by moment. It is a perspective that unsettles as much as it fascinates. What made Minkowski's contribution so powerful was not just the mathematics, but the clarity it brought. Einstein's equations were like notes of music on a page, complex and brilliant. Minkowski turned them into a symphony, showing how each note fit into the larger harmony. Suddenly, relativity was not only a set of rules for moving clocks and contracted lengths, but a vision of the universe itself as a fabric where all events were interwoven. This new framework did more than tidy up Einstein's results. It opened the door to fresh discoveries. The light cone naturally explained why nothing could outrun light. World lines clarified how time and space transformed for moving observers. The geometry of space-time began to suggest new possibilities that had not been dreamt of before. Within a few years, Einstein would take this framework and bend it further, imagining not only a space-time that connected space and time, but one that could curve and warp itself under the influence of mass and energy. Minkowski himself did not live to see how far his idea would go. He died unexpectedly in 1909 at the age of only 44, just as his vision was beginning to reshape physics. Yet his unification of space and time into a single entity laid the foundation for modern physics. Every time we speak of space-time, of world lines, of light cones, we echo the leap of imagination he made in that Cologne lecture. It is a reminder that sometimes physics advances not only through experiments, or even through equations, but through a new way of seeing. Minkowski gave us a language to picture what Einstein had revealed, and in doing so he changed how we conceive the universe itself. The familiar backdrop of space and the ticking of time dissolved into a greater whole, leaving behind a cosmos more unified and mysterious than anyone in Newton's day could have imagined. In 1915, Albert Einstein unveiled an idea that would forever alter the way we see the universe. After years of relentless thought, trial and error, he introduced his general theory of relativity. If special relativity had shown that space and time were linked together into a four-dimensional fabric, general relativity revealed that this fabric was alive. It could bend, warp, stretch, and ripple. Gravity, long thought of as a mysterious force pulling objects toward one another, was reimagined as the very shape of space-time itself. To appreciate just how bold this was, think about how people had understood gravity up until then. Isaac Newton had given the world a law of universal gravitation in the 17th century. In his view, every mass attracted every other mass with a force, one that weakened with distance but never disappeared entirely. The apple fell from the tree because the Earth pulled it. The moon orbited the Earth because Earth's gravity tugged at it, even across hundreds of thousands of kilometers of empty space. Newton never explained how this force acted at a distance. It just did. He gave the world an equation, and the equation worked. But Einstein wanted something deeper. Einstein began wondering, what if gravity wasn't a force at all? He was guided by what he called the equivalence principle. Imagine standing in an elevator. If the cable snapped and you began to fall, you would feel weightless. Your body would float inside the elevator just as astronauts do in orbit. To Einstein, this hinted at something profound. Being in freefall was indistinguishable from floating freely in space. Gravity could be mimicked by acceleration, and acceleration could be seen as indistinguishable from gravity. This equivalence suggested that gravity was not a mysterious tug between objects, but a property of space-time itself. In general relativity, Einstein proposed that matter and energy tell space-time how to curve, and curved space-time tells matter how to move. Planets do not orbit the Sun because the Sun pulls them by an invisible force. They orbit because the Sun's immense mass warps space-time, and the planets follow the natural curved paths in this distorted geometry. What looks like a force is really geometry at work. The most common way this is explained is with the famous rubber sheet analogy. Picture a large rubber sheet stretched taut. If you place a heavy ball in the middle, the sheet sinks and curves around it. If you then roll a smaller ball nearby, it spirals inward toward the larger ball, not because the larger ball is directly pulling it, but because the sheet's shape guides its motion. This simple picture has helped generations of students picture Einstein's idea. But it comes with limits. Real space-time is not a two-dimensional sheet in a higher space. It is the fabric of the universe itself. The rubber sheet only curves downward because of gravity acting in yet another dimension. True space-time curvature is intrinsic. It does not need an extra dimension to bend into. The analogy is useful, but the reality is stranger and more subtle. Still, the idea that space and time could bend was revolutionary. Imagine a beam of light passing near a massive star. In Newton's world, light had no mass and therefore should not feel gravity. In Einstein's world, light would still follow the straightest possible path through space-time. But if space-time itself was curved, that straightest path, what mathematicians call a geodesic, would bend along with it. The prediction was clear. Starlight passing near the Sun would be deflected ever so slightly. Einstein's equations of general relativity were not easy to derive. He struggled for nearly a decade, refining his ideas, making mistakes, discarding false starts, and returning again to the math. By November of 1915, he finally presented the complete theory to the Prussian Academy of Sciences. His equations were elegant and concise, describing how matter and energy warped the geometry of space-time. These equations would go on to explain everything from planetary motion to the behavior of black holes. One of the most striking features of Einstein's theory is that space-time is not a passive stage. In Newton's universe, space was the rigid backdrop against which celestial bodies moved. In Einstein's universe, space-time itself was dynamic. It responded to matter and energy. It could ripple like a pond struck by a stone. It could stretch, shrink, and even expand. The stage had become an actor. This shift in perspective was as much philosophical as scientific. Space and time were no longer absolutes, fixed and immutable. They were flexible, responsive, and intertwined with the very stuff of the cosmos. If the Sun suddenly vanished, a purely hypothetical thought experiment, the planets would not feel an instantaneous loss of gravity, as Newton's law suggested. Instead, a disturbance would ripple outward through space-time at the speed of light. Gravity had a speed, and that speed was finite. Einstein's theory also explained long-standing puzzles. Mercury's orbit around the Sun did not quite match predictions from Newton's laws. The discrepancy was tiny, but astronomers had noticed it for decades. General relativity explained it perfectly as a result of space-time curvature near the Sun. It was a triumphant moment for the new theory, showing it could succeed where Newton had fallen short. The elegance of general relativity lies in its simplicity. Matter tells space-time how to curve, curved space-time tells matter how to move. This back-and-forth relationship is like a cosmic conversation, a dance between geometry and energy. It is a view of the universe where everything is interconnected, not by invisible forces acting at a distance, but by the shape of the very stage on which existence unfolds. At first, the world was slow to accept Einstein's ideas. They were difficult to test and required a new way of thinking, but the seeds were planted. Space-time was no longer something to take for granted. It had become a participant in the cosmic drama, bending and flexing with every star and planet. The static stage of Newton had given way to a living fabric, one that could carry the weight of the cosmos and shape the destiny of worlds. What Einstein delivered in 1915 was not just a theory of gravity, but a new way of conceiving reality. It revealed that the universe is not built upon rigid scaffolding, but upon a flexible geometry that responds to everything within it. In that geometry lies the story of falling apples, orbiting planets, bending starlight, and ultimately the fate of the cosmos itself. When Einstein first proposed general relativity in 1915, it was a theory so bold that many scientists struggled to believe it. The mathematics was elegant, but elegant mathematics can sometimes lead you astray. What the world needed was proof, something to show that space-time really does bend under the weight of matter. That proof arrived just a few years later, thanks to a daring expedition to chase the shadow of the moon. In 1919, the British astronomer Arthur Eddington led a team to observe a total solar eclipse. Einstein had predicted that light passing near a massive body, like the Sun, would be bent by the curvature of space-time. Stars that appeared close to the Sun's edge in the sky should look as though they had shifted position. The eclipse provided the perfect opportunity to test this idea, since the Sun's blinding glare would be hidden long enough for astronomers to take photographs of the stars near its rim. Eddington travelled to the island of Principe off the west coast of Africa, while another team set up in Brazil, each hoping for clear skies. On May 29th, as the moon slid across the Sun, cameras clicked furiously. Later the plates were developed and measured. The starlight had indeed shifted just as Einstein predicted. The amount of bending matched his equations almost perfectly. Newspapers around the world declared Einstein a scientific superstar overnight, splashing headlines like "Revolution in Science" across their front pages. For the first time, humanity had caught space-time in the act of curving. That dramatic eclipse was just the beginning. Over the years, more subtle and powerful confirmations of relativity began to accumulate. One of the most spectacular is gravitational lensing. If space-time curves around a massive object, then light passing by should follow that curve, much like a lens bends light in an optical instrument. A galaxy, or a cluster of galaxies, can therefore act as a natural telescope, magnifying and distorting the light of objects behind it. Seen through powerful observatories, these cosmic lenses create breathtaking images. A single quasar can appear doubled or quadrupled, its light split into multiple paths by an intervening galaxy. Sometimes entire galaxies are smeared into long arcs of light. In the most striking cases, you can even see an Einstein ring, a perfect circle of light formed when a distant object lines up directly behind a massive foreground lens. These cosmic distortions are not flaws in the fabric of space, but windows into its geometry. Each bent beam of light is a silent testimony to the truth of curved space-time. Gravitational lensing is more than a curiosity. It has become one of the most powerful tools in modern astronomy. By studying how much light is bent, scientists can map the distribution of mass in galaxies and clusters, including the invisible dark matter that outweighs ordinary stars by a vast margin. Without general relativity, these lenses would make no sense. With it, they become natural laboratories, letting us study both the seen and the unseen universe. Yet proof of relativity is not confined to exotic eclipses or distant galaxies. You carry it in your pocket every day, quietly working away in the background. The Global Positioning System, or GPS, relies on satellites orbiting high above the Earth. Each one carries an atomic clock, precise enough to lose less than a billionth of a second in a day. For GPS to work, those clocks must remain synchronized with those on the ground. Here is where Einstein steps in. Because the satellites are moving quickly relative to the Earth, special relativity tells us their clocks should run a little slow. At the same time, because they are farther from Earth's mass, general relativity predicts that space-time is less curved there, so their clocks should actually run a little fast. These two effects, one slowing time and the other speeding it up, do not cancel out. The net result is that the clocks in orbit tick faster than those on Earth by about 38 microseconds each day. That may not sound like much, but even a tiny error in timing translates into huge errors in position. A difference of just 1 microsecond means a positioning error of hundreds of meters. Without correcting for relativity, your phone would tell you that you were standing somewhere in the wrong city block, or even in the wrong town altogether. Thanks to Einstein's equations, the GPS system compensates for both effects, keeping your location accurate down to a few meters. Next time you use your phone to find the nearest coffee shop, remember that you're relying on the warping of space-time to get there. In a way, every smartphone is a relativity device. The story of testing curved space-time is one of the most remarkable in science, because it moves so seamlessly from the grandest scales to the most ordinary moments of daily life. From the shadow of the moon during an eclipse to arcs of light painted across the sky by distant galaxies, to the device buzzing in your hand, Einstein's theory has shown itself to be more than an abstract set of equations. It is a description of the world we live in, accurate across scales that range from the cosmic to the everyday. What began as a daring theoretical leap in 1915 was vindicated just 4 years later by Eddington's photographs of bent starlight. Since then, every test has confirmed the same truth. Space-time curves, and that curvature shapes the path of light, the ticking of clocks, and the motion of planets. With each confirmation, our picture of reality grows stranger, but also more precise. Einstein may not have lived to see satellites beaming directions to phones in every pocket, but he would not have been surprised that his vision of a dynamic space-time had become part of ordinary human life. In the early decades of the 20th century, astronomers thought of the universe as vast but essentially static. Stars and nebulae twinkled against the dark canvas of the sky, and the general belief was that the cosmos had always looked much as it does now. The idea that the universe might be expanding and that space-time itself was stretching was almost unthinkable. Yet evidence was quietly gathering, waiting for someone with the patience to notice. That someone was Edwin Hubble, working at Mount Wilson Observatory in California in the 1920s. Using the powerful Hooker telescope, Hubble studied faint fuzzy patches of light that many believed were just nearby gas clouds. With the help of Henrietta Leavitt's work on variable stars, he was able to show that these patches were not clouds within our galaxy at all, but entire galaxies in their own right, millions of light years away. The universe, it seemed, was far larger than anyone had dared imagine. But Hubble's most remarkable discovery came when he compared the light from these galaxies. He noticed that their spectra, the rainbows of light spread into bands, were shifted toward the red end. This redshift suggested the galaxies were moving away from us. More than that, the farther away a galaxy was, the faster it appeared to be receding. The relationship was strikingly linear, a pattern now known as Hubble's law. It was as if the entire universe was stretching. At first glance, it is tempting to picture galaxies flying through space like shrapnel from an explosion. But that picture is misleading. In Einstein's framework, it is not galaxies racing outward through an existing void. Instead, it is space-time itself that expands. The fabric of the cosmos stretches, carrying galaxies along with it. Imagine raisins baked into a loaf of bread. As the dough rises, the raisins move apart, not because they are crawling away from each other, but because the dough between them is swelling. The galaxies are not projectiles hurtling through emptiness. They are passengers on the ride of expanding space-time. This change in perspective is crucial. It explains why there is no true center to the expansion. Every observer, wherever they are, sees other galaxies moving away, just as every raisin in the loaf sees other raisins receding. So every galaxy sees the universe stretching around it. Space is not an empty container, but a dynamic fabric, reshaping itself as time passes. The implications of this discovery were staggering. If the universe is expanding now, it must have been smaller in the past. Wind the clock backward, and all of space and time collapse to a point. This was the origin of what we now call the Big Bang, the beginning not only of matter and energy, but of space-time itself. There was no before, because time itself began at that moment. There was no empty void into which the universe exploded. The expansion was the growth of space-time from a state of unimaginable density and heat. The Big Bang was not an explosion in space, it was an explosion of space. This is one of the hardest ideas to wrap one's head around, because everyday experiences offer no real analogy. Fireworks burst into a pre-existing sky. Dust spreads into a pre-existing room. But the cosmos was not expanding into anything. It was creating the stage as it went. Time ticked forward only from that moment. Space stretched outward, only from that moment. To ask what happened before the Big Bang is to ask what lies north of the North Pole. The question dissolves once you understand the terms. As the universe expanded, it cooled, allowing the formation of atoms, stars, and galaxies. Structures that now fill the night sky are the byproducts of spacetime's growth. The ripples we see in the cosmic microwave background, the faint afterglow left from the early universe, are direct evidence of that expansion, frozen into light that has travelled for nearly 14 billion years. It is hard not to feel a sense of awe at this. Every star you see, every planet, every atom in your body, all arose within this expanding fabric. We are part of a story that began when space-time itself came into being, a story that continues with each moment the cosmos grows larger. The discovery of the expanding universe also reshaped our sense of scale. Instead of a static cosmos, infinite and eternal, we now know we live in one that is dynamic and evolving. Galaxies drift farther apart with every passing second. Distances we measure today will be greater tomorrow. On human timescales, the effect is imperceptible, but over billions of years it transforms the entire structure of the cosmos. Even today, astronomers measure the rate of expansion with increasing precision, debating the exact value of the Hubble constant. Some measurements based on distant supernovae and galaxies suggest one rate, while others based on the cosmic microwave background suggest another. The tension between these values is one of the great puzzles of modern cosmology, hinting that there may still be something missing from our understanding of spacetime's behaviour. But the core insight remains: space-time is not static. It is elastic, stretching and reshaping itself, carrying galaxies along like leaves drifting on a cosmic tide. When we look at the deep sky through powerful telescopes, we are not only seeing distant objects, we are looking back through time at earlier moments of this stretching fabric. The light that arrives to our eyes tonight began its journey billions of years ago, across a cosmos that has been expanding the entire way. The realization that the universe is expanding transformed physics, astronomy, and philosophy. It showed that reality itself has a history, a beginning, and perhaps a future end. It turned space-time from a backdrop into an actor, shaping not only the paths of planets and stars, but the very scale of the cosmos. The quiet work of Edwin Hubble and his telescope opened the door to a vision of the universe far more dramatic than anyone expected. A universe born from the stretching of space-time, still growing, still unfolding, and still carrying us along on its endless journey. The word horizon, usually makes us think of the line where the sea meets the sky, a distant boundary that shifts as we move but always stays just out of reach. In physics, horizons carry a similar sense of mystery. They mark the edges of what can be seen, known, or influenced. In space-time, horizons are not merely poetic, they are fundamental limits, drawn not by geography, but by the structure of reality itself. The most famous of these boundaries is the event horizon of a black hole. Imagine a star collapsing under its own gravity, squeezing tighter and tighter until its matter is crushed beyond recognition. As the star shrinks, the gravity at its surface grows stronger, until eventually not even light can escape. The distance from the centre where this occurs is the event horizon. It is not a physical surface you could bump into, but rather a point of no return. Once you cross it, all paths forward lead inward, toward the singularity. To an outside observer, the event horizon appears frozen in time. A spaceship falling toward it seems to slow down, its clocks ticking ever more sluggishly, its light stretching to redder and redder wavelengths. The craft never quite crosses from the outside point of view, but for the traveller inside, nothing dramatic happens at the horizon itself. They sail past in a fraction of a second, unaware that they have stepped over a cosmic boundary from which there is no escape. Horizons are like that. They depend on perspective. Black holes are not the only places where horizons appear. The universe itself has a horizon too, a cosmological one. Because light travels at a finite speed, we can only see as far as light has had time to reach us. With the universe about 13.8 billion years old, you might think our horizon would be that distance. But because space-time has been expanding, the true edge of what we can see is much farther away, around 46 billion light-years in every direction. Beyond that horizon, there may be countless galaxies, perhaps infinite space, but their light has not yet reached us, and it never will. The horizon is not a wall but a limit set by time, distance, and the expansion of space-time. This cosmological horizon creates a kind of observable bubble around us. Everything we know about the universe comes from within that bubble. Beyond it lies the unobservable, forever hidden. And yet, in a sense, every observer in the universe carries their own bubble. An alien on a distant galaxy would see their own horizon, centered on them, containing their own slice of the cosmos. Horizons are not unique to us. They are a universal feature of living in an expanding space-time. There is another kind of horizon, less famous but no less fascinating, the Rindler horizon. This one is tied to acceleration. Imagine a spaceship firing its engines, accelerating faster and faster. For the passengers inside, something peculiar happens. Because of the finite speed of light, there will be regions of the universe behind them from which signals can never catch up. No matter how long they wait, no matter how brightly a distant star shines, its light will never reach the accelerating ship. The boundary that divides what can be seen from what is lost forever is the Rindler horizon. What makes Rindler horizons intriguing is that they are not tied to the structure of the universe as a whole, nor to collapsed stars, but to the experience of the observer. To someone standing still, the star is visible. To the accelerating astronaut, it is gone forever. Horizons, it seems, are not absolute boundaries carved into the cosmos, but relative ones, defined by motion and perspective. Each of these horizons, the event horizon of a black hole, the cosmological horizon of the universe, and the Rindler horizon of acceleration, tells us something profound about space-time. They remind us that what we can observe is limited not only by the reach of our telescopes, but by the fundamental geometry of reality. There are things we simply cannot see, not because they are hidden behind walls, but because the structure of space-time makes them unreachable. And yet, horizons are not purely barriers. They also shape the universe in subtle ways. The event horizon of a black hole is tied to the black hole's entropy and temperature, concepts that hint at deep connections between gravity, thermodynamics, and quantum mechanics. The cosmological horizon defines the edge of the observable universe, but it also sets the scale for cosmic microwave background radiation, the faint afterglow of the Big Bang. The Rindler horizon leads to predictions such as the Unruh effect, where accelerating observers would perceive a warm bath of particles in what others call empty space. These are not just theoretical curiosities, they challenge our understanding of what it means to know something at all. If parts of the universe lie beyond our horizon, are they part of reality? If different observers have different horizons, can we say what the universe really is in a universal sense? Horizons force us to confront the limits of knowledge and the role of perspective in physics. The beauty of horizons lies in their dual nature. They are both boundaries and guides. They tell us where our knowledge ends, but they also point the way to deeper truths. When Einstein described space-time as dynamic, horizons emerge naturally as features of that dynamism. They are the edges of possibility, the lines beyond which our current understanding cannot reach. In daily life, the horizon is something we can walk toward, even sail beyond, only to find another horizon waiting. In space-time, the horizons we face are more stubborn. No amount of walking or sailing or waiting will carry us past them, and yet, within those limits, the universe unfolds with endless richness. Black holes curve space-time into cosmic traps. The universe expands beyond what we can see, and acceleration itself can create unreachable regions of reality. Horizons may mark our boundaries, but they also remind us that within those boundaries lies a universe full of wonder. In 1916, only a year after finishing his general theory of relativity, Albert Einstein made a bold prediction. If space-time could bend and curve under the influence of mass, then perhaps it could also ripple. Just as dropping a stone in a pond creates waves spreading outward across the surface, Einstein suggested that violent events in the universe might send out waves in the very fabric of space-time itself. These ripples, called gravitational waves, would carry energy across the cosmos at the speed of light. The idea was elegant, but there was a catch. Gravity is incredibly weak compared to the other forces of nature, and Einstein himself doubted whether such waves would ever be detectable. To stir space-time enough to create noticeable ripples, you would need catastrophic events on a cosmic scale. Colliding stars, collapsing black holes, titanic explosions. Even then, by the time the waves reached Earth, they would distort space by less than the width of a single atom. Detecting them would require technology far beyond anything available in Einstein's lifetime. For decades, gravitational waves were little more than a theoretical curiosity, hovering on the border between physics and imagination. The search began in earnest in the second half of the 20th century. In the 1960s, physicist Joseph Weber built massive aluminum cylinders known as Weber bars, hoping they would vibrate ever so slightly when struck by passing gravitational waves. The results were inconclusive, and many scientists doubted whether the waves would ever be seen. But the idea refused to die. Across the world, physicists began building ever more sensitive detectors, convinced that the universe's hidden symphony was out there, waiting to be heard. The most ambitious of these projects became known as LIGO, the Laser Interferometer Gravitational Wave Observatory. Built with two enormous facilities, one in Louisiana and the other in Washington state, LIGO uses laser beams sent down 4-kilometer-long tunnels arranged in an L shape. The beams bounce back and forth between mirrors, and if a gravitational wave passes through, it would stretch one arm of the L ever so slightly while squeezing the other, changing the interference pattern of the light. The challenge was staggering, measuring distortions of less than 1/10,000th the width of a proton. Many thought it was impossible, and yet on September 14, 2015, after decades of preparation, LIGO finally caught the whisper of space-time itself. Two black holes, each about 30 times the mass of the Sun, had collided over 1 billion light-years away. The violent merger sent ripples surging across the universe, and after travelling for more than 1 billion years, they gently brushed past the Earth. LIGO's detectors twitched with the faintest of signals, a tiny chirp in the data, marking humanity's first direct detection of gravitational waves. The news electrified the scientific world. Einstein's century-old prediction had been confirmed, and a new era of astronomy was born. No longer were we limited to studying the universe through light, radio waves, or X-rays. We now had a way to listen to the cosmos through the vibrations of space-time itself. Gravitational wave astronomy opened a new sense, like suddenly being able to hear after a lifetime of silence. Since that first detection, LIGO and its sister observatories, such as Virgo in Italy and Kagra in Japan, have recorded dozens more events. Most come from the mergers of black holes, where space-time shakes violently as the objects spiral together. Each collision sends out a final burst of waves that rise in pitch and then abruptly cut off, a cosmic chirp announcing the birth of a new, larger black hole. Even more dramatic was the detection in 2017 of 2 neutron stars colliding. Unlike black holes, neutron stars are made of matter, dense, exotic matter, squeezed to extremes. When they spiral into one another, they not only produce gravitational waves but also enormous bursts of light and radiation. For the first time, astronomers were able to watch an event both through telescopes and through gravitational wave detectors. The collision lit up the sky with gamma rays, radio waves, and visible light, while LIGO recorded the space-time ripples. This event confirmed theories about where heavy elements like gold and platinum come from. They're forged in the fiery furnaces of neutron star mergers and then scattered across the cosmos. Every ring on your finger carries within it the echo of a cosmic catastrophe billions of years old. What makes gravitational waves so special is that they give us access to phenomena hidden from ordinary light. Black holes, by definition, emit no light. Collisions in the distant universe might be shrouded in dust and gas, invisible to telescopes, but gravitational waves pass through matter unimpeded. They carry pristine information about the events that created them, like messengers from realms otherwise beyond our reach. Physicists often speak of the sound of space-time, because gravitational waves are recorded not only as squiggles in data, but also as frequencies that can be shifted into the range of human hearing. The result is eerie and beautiful. A series of chirps and whoops that sound almost like drops of water or plucked strings. These are the voices of black holes, neutron stars, and perhaps someday, even the faint hum left over from the Big Bang itself. Listening to gravitational waves is like discovering that the universe has been playing music all along, and only now do we have the ears to hear it. The hidden symphony of space-time has only just begun to be explored. Future detectors, including space-based observatories like LISA, the Laser Interferometer Space Antenna, will open new frequency ranges, listening for waves from supermassive black holes at the centres of galaxies, and perhaps even the ripples created in the first moments after the universe began. With each detection, we not only confirm Einstein's vision, but also extend it, revealing a cosmos more dynamic and vibrant than he could have imagined. What began as a tentative prediction in 1916 has become a new branch of science, one that lets us study the universe not just as a picture, but as a performance. The ripples of space-time are the drumbeats of black holes, the crescendos of neutron stars, and the lingering chords of cosmic history. They remind us that the universe is not silent. It is filled with rhythm, vibration, and song, written not in notes on a page, but in the waves of space-time itself. A black hole is one of the strangest predictions ever to come out of Einstein's theory of general relativity. It is not just a heavy star or an exotic object hidden away in space. It is a region where space-time itself is pushed to extremes. In fact, the very definition of a black hole comes not from the matter it contains, but from the geometry of space-time around it. A black hole is a place where space-time is so curved that all paths forward lead inward. At its boundary lies the event horizon, the point of no return. This horizon is not a solid surface but a mathematical boundary in space-time. For an outside observer, nothing that crosses it can ever come back out, not even light. The geometry of space-time is so warped that all future directed paths curve inward. In ordinary life, when you toss a ball, you can choose where to aim, and gravity simply pulls the ball along a curved arc. Near a black hole, choice disappears. The very geometry that defines what forward in time means has been twisted so that all futures point deeper inside. This makes black holes profoundly different from other celestial bodies. A planet or star can be described by its mass, size, and composition. A black hole, in contrast, is described almost entirely by space-time geometry. Remarkably, the mathematics tells us that a black hole can be completely characterized by just a few numbers: its mass, its spin, and its electric charge. This is sometimes called the no-hair theorem. In other words, black holes are bald. They forget all details of the matter that formed them and retain only those basic traits. Whether a black hole was born from a collapsing star or from the merger of other black holes does not matter. Once it forms, its history is erased, leaving behind only pure geometry. Inside the event horizon lies the singularity, a place where the mathematics of general relativity breaks down. At the singularity, space-time curvature becomes infinite, and the familiar laws of physics cease to function. This is not simply a very dense star at the centre. According to relativity, the singularity is not even a point in space as we normally understand it. It is a point in time, an unavoidable destination for anything that crosses the horizon. Once inside, all paths lead to the singularity, and there is no turning back. Singularities are where space-time itself seems to tear. They signal the limit of Einstein's equations, the places where geometry collapses under its own weight. Many physicists believe that a complete theory of quantum gravity, uniting relativity with quantum mechanics, will eventually smooth out the singularity into something more comprehensible. But for now, singularities remain mysterious abysses at the heart of black holes. Despite their reputation as devourers of matter, black holes are not entirely dark. In the 1970s, Stephen Hawking applied the principles of quantum mechanics to the curved space-time around a black hole and made a surprising discovery. Black holes should emit radiation. This effect, now called Hawking radiation, arises from the quantum nature of the vacuum itself. In quantum physics, empty space is not truly empty. It seethes with pairs of particles and antiparticles that flicker into existence and then annihilate almost instantly. Near the event horizon of a black hole, one of these particles can fall inside while the other escapes. To a distant observer, it appears as though the black hole is radiating energy. Over immense timescales, this process allows black holes to slowly evaporate, losing mass bit by bit until they may eventually vanish. Hawking radiation is extraordinary because it brings together the two great frameworks of modern physics: general relativity, which governs space-time and gravity, and quantum mechanics, which governs the microscopic world. Normally, these two theories live in separate realms, but at the edge of a black hole they collide, producing insights that hint at a deeper, unified description of reality. This evaporation has profound implications. It means black holes are not eternal prisons, but temporary structures with lifespans. A small black hole could vanish in a flash of high-energy radiation. Larger ones take far longer. Supermassive black holes at galactic centers would take more than a Google years to evaporate, far longer than the current age of the universe. Still, the idea that even the most extreme objects in the cosmos are ultimately impermanent is a humbling thought. Hawking radiation also raises puzzles. If black holes evaporate, what happens to the information about the matter that fell in? Does it vanish as well, violating one of the central rules of quantum physics? or is the information somehow encoded in the radiation that escapes? This black hole information paradox remains one of the greatest unsolved mysteries in physics. Some suggest that the horizon itself stores information like a hologram. Others propose that new physics entirely is required to resolve the contradiction. What is clear is that black holes are no longer thought of as simple dead ends of collapsed stars. They are laboratories of the extreme, where space-time, matter, energy and quantum rules meet and clash. Their horizons are boundaries in geometry, their singularities are hints of new physics waiting to be discovered, and their radiation is a whisper from the interface of the quantum and the cosmic. In the popular imagination, black holes are monsters lurking in the darkness, sucking up anything that dares come close. In reality, they are elegant predictions of Einstein's mathematics, sculpted from the shape of space-time itself. They are destructive, yes, but also creative, powering quasars and shaping the growth of galaxies. They are cosmic puzzles, asking questions that stretch human thought to its limits. To contemplate a black hole is to look at space-time in its rawest form, torn and twisted to the edge of comprehension. These objects remind us that the universe is not only stranger than we imagine, but stranger than we can imagine. They are places where geometry becomes destiny, where the smooth fabric of reality is pulled into knots, and where even the laws of physics must eventually give way. The universe is vast, so vast that even light, the fastest thing we know, takes years, centuries, or even billions of years to cross the gulfs between stars and galaxies. Faced with these staggering distances, it is natural to wonder, might there be a shortcut? Could space-time itself contain tunnels or bridges that connect faraway places, letting us slip through, like stepping into a hidden passageway? This idea is not only the stuff of science fiction, but also a serious question in physics, and it goes by the evocative name of wormholes. The seeds of the concept can be found in Einstein's general relativity. In 1935, Einstein and his colleague Nathan Rosen explored the mathematics of black holes and found something curious. Their equation suggested that certain solutions looked like bridges, what we now call Einstein-Rosen bridges, linking two separate regions of space-time. Imagine two funnels facing each other, their narrow ends touching. Each funnel is a black hole, and the point where they meet is a throat connecting them. Pass through the throat and in principle you emerge somewhere else entirely. At first glance, this sounded like exactly the kind of cosmic shortcut that daydreaming travellers might wish for. But there was a catch. The Einstein-Rosen bridge was not stable. In fact, it would pinch shut faster than any light or spaceship could cross it. The bridge was a mathematical curiosity, but it seemed useless for practical travel. Still, the idea of space-time tunnels had been planted, and physicists kept wondering, could there be a way to hold such a tunnel open? That line of thought gave birth to the idea of traversable wormholes. The mathematics suggests that, if you could find a way to keep the throat of the wormhole from collapsing, you could, in theory, pass through. The trick would be finding a kind of material with negative energy density, often called exotic matter. Unlike ordinary matter, which curves space-time inward with its gravity, exotic matter would push outward, counteracting the collapse of the wormhole and holding it open. Exotic matter is not something you can scoop up at the local hardware store. It is speculative, fragile, and in many cases may not exist in the quantities needed. Certain effects in quantum physics do produce negative energy densities in tiny amounts, but scaling this up to cosmic proportions would be unimaginably difficult. Without such exotic matter, a wormhole remains a fleeting flicker in the equations, snapping shut before it can be used. Even if exotic matter could be conjured, wormholes present other problems. They might allow faster-than-light travel, at least in appearance, by creating a shortcut between distant points. But faster-than-light travel invites paradoxes. Could you arrive before you left? Could wormholes be twisted into time machines, sending messages or travellers backward in time? These questions are not just science fiction headaches. They are real puzzles in the logic of physics. Some physicists suspect that the universe itself forbids such paradoxes, destroying wormholes before they could lead to violations of causality. Despite these challenges, wormholes have captured the imagination of scientists and storytellers alike. They embody the dream of escaping the tyranny of distance, of finding hidden doors in the fabric of the cosmos. Popular culture has embraced them with enthusiasm. In movies like Interstellar, wormholes are depicted as shimmering spheres, gateways that allow travellers to step across galaxies in moments. The film consulted physicist Kip Thorne, who helped design a scientifically plausible version of a wormhole for the screen. While the movie took liberties, the visuals were grounded in real physics, showing how light would distort and swirl around such a tunnel. The fascination is easy to understand. The idea that the universe might contain natural shortcuts makes the impossible feel just a little closer. Wormholes offer a glimpse of hope in a cosmos otherwise dominated by the slow crawl of light and the vast emptiness between stars. They whisper of adventures waiting just beyond the horizon, of doors to other places, or even other universes, hidden in the folds of space-time. Yet the sober truth is that wormholes remain speculative. None have ever been observed, and the conditions required for their existence are extreme. It is possible they are ruled out entirely by the deeper laws of physics, and that they remain forever in the realm of thought experiments and storytelling. Still, their presence in the equations reminds us that space-time is not as rigid as it first appears. It can curve, twist, ripple, and perhaps, under the right conditions, even fold in on itself to make tunnels. What makes wormholes such an enduring topic is that they sit at the boundary of imagination and science. They're grounded enough in real physics to be taken seriously, but strange enough to inspire wonder. Even if they never prove practical, the very act of thinking about them stretches our understanding, forcing us to grapple with what space-time can and cannot do. In that way, wormholes serve as intellectual wormholes of their own, carrying us from the familiar into realms of thought we might never have reached otherwise. So while no spaceship has yet leapt across the galaxy through a hidden tunnel, the idea continues to inspire both science and story. Wormholes are reminders that the universe may be richer and stranger than we imagine, full of paths and possibilities folded into its fabric. Whether they exist as real doorways or remain forever as beautiful mathematics, they stand as symbols of curiosity itself, the desire to find shortcuts not only through space-time but through the limits of our own imagination. Time is something we all feel we know. It seems to flow like a river, carrying us from past to present to future. The seconds tick, the days pass, and we march forward with them. Yet when we look at time through the lens of space-time, that familiar flow begins to look less certain. In Einstein's picture of the universe, time does not move. It simply is. Past, present, and future are all woven into the same four-dimensional fabric, existing together like pages in a book. This vision is sometimes called the block universe. Imagine the cosmos not as a movie playing frame by frame, but as the entire reel of film existing all at once. Each moment, your first day at school, the orbit of the moon tonight, the death of the sun billions of years in the future, is a frame already there in the block. From our perspective as conscious beings, we experience those frames one at a time, like readers scanning a story word by word. But in the block view, every event exists equally, waiting in its own coordinate of space-time. It is a deeply unsettling idea. If the future is already there in the block, does that mean it is fixed? Do we have no free will? Physics does not answer those questions directly, but it shows us that the universe does not privilege the now the way we think it does. The present moment in relativity is not universal. Two observers moving differently may disagree on whether two events happened at the same time. What we call now is a local slice through the block, unique to each observer. There is no cosmic clock ticking in unison for everyone. Still, our experience tells us time has a direction. We remember the past but not the future. We can influence what happens tomorrow, but not what happened yesterday. Tea cools in the cup but never spontaneously warms itself. The block may contain every moment equally, but within it there is an arrow of time, a sense of before and after that shapes our lives. Where does this arrow come from? One answer lies in entropy, the measure of disorder in a system. The second law of thermodynamics tells us that entropy tends to increase. Eggs break but do not unbreak. Smoke disperses but does not gather itself back into the fire. From the perspective of physics, this steady climb in entropy is what gives time its direction. The past was ordered, the future is disordered, and the flow we feel is simply the march from low entropy to high. Why was the past low in entropy in the first place? That is a question that still puzzles cosmologists. The early universe, immediately after the Big Bang, was remarkably smooth and uniform, a state of extraordinarily low entropy. Over time, structure formed, stars lit up, and the complexity we see today unfolded. But the fundamental reason why the cosmos began in such an ordered state remains a mystery. Some suggest it is simply a brute fact, others that it may hint at deeper principles we have not yet discovered. The arrow of time also reveals itself in how we process memory. We remember what has already happened, but not what has yet to come. Physics itself makes no distinction between past and future. The equations work the same in both directions. A movie of particles bouncing around could be played backward, and the math would not complain. Yet our minds insist on a forward direction. The reason, again, is entropy. Recording a memory, whether in neurons or in ink, requires energy. It creates disorder in the surrounding environment. Remembering always increases entropy, so it can only point backward, to states of lower entropy that have already occurred. This explains why we do not recall the future, even though in the block universe it exists as surely as the past. Our mental arrow of time is bound to the thermodynamic arrow, stitched into the physics of energy and disorder. Memory and causality ride the same current. We can know what happened, we can influence what happens next, but the future only reveals itself when we get there, frame by frame, in a sequence that feels like flow. Of course, our daily sense of time's passage remains powerful. Clocks tick, calendars turn, and our bodies age. But in the deep view of space-time, the river may not be flowing at all. The river simply exists, every bend and stretch already laid out, with us drifting along its course not because time flows, but because our consciousness moves from one slice of the block to the next. This tension between physics and perception makes time one of the most fascinating aspects of space-time. The block universe shows us a reality where past, present, and future are equally real, frozen into the fabric of space-time. Thermodynamics and entropy give that block its direction, a gradient from order to disorder, and our memories give it texture, anchoring us to the past while leaving the future hidden. Whether or not time truly flows, or whether it only seems to flow to beings like us, remains a question as much philosophical as scientific. What is certain is that time in space-time is not the simple, ticking metronome Newton once imagined. It is stranger, subtler, and perhaps more beautiful. A tapestry where every moment is woven in, but where we, like threads, only pass across it once. Modern physics rests on two towering pillars. One is Einstein's theory of relativity, which describes gravity and the large-scale structure of space-time. The other is quantum mechanics, which governs atoms, particles, and the strange world of the very small. Each theory is dazzlingly successful in its own domain. Relativity explains the orbits of planets, the bending of light, and the evolution of galaxies. Quantum mechanics explains the structure of matter, the behavior of electrons, and the workings of modern technology from semiconductors to lasers. But there is a problem. These two theories do not fit neatly together. They are like two beautifully carved puzzle pieces that stubbornly refuse to lock. Relativity treats space-time as a smooth, continuous fabric. Mass and energy bend it, and objects move along the resulting curves. Quantum mechanics, on the other hand, describes reality as inherently grainy, with particles flickering in and out of existence and uncertainty baked into every measurement. When physicists try to bring quantum ideas into curved space-time, the mathematics often explodes into infinities that make no physical sense. Gravity, when quantized like the other forces, misbehaves. The two great theories are not enemies exactly, but they seem to be speaking different languages. One way to think of the problem is this. In quantum physics, fields live on space-time. The electromagnetic field, for instance, stretches across the universe, with photons as its quanta. The strong and weak nuclear forces are described in a similar way. These fields ripple and fluctuate, but they always need a stage to ripple on. Relativity tells us that the stage itself, space-time, is dynamic. It bends, stretches and curves in response to mass and energy. So which is it? Is space-time the backdrop for quantum fields? Or is it an actor in the drama itself? If space-time can fluctuate, then the very ground on which quantum theory is built is unstable. At everyday scales, this conflict does not trouble us. Satellites orbit the Earth just as relativity predicts, and atoms behave just as quantum mechanics describes. But push into the extremes, and the clash becomes unavoidable. Consider the centre of a black hole, where gravity crushes matter into a singularity. Relativity says space-time curvature becomes infinite there, while quantum mechanics refuses to accept infinities as physical. Or consider the first fraction of a second after the Big Bang, when the universe was so small and dense that both quantum effects and space-time curvature were enormous. To describe those conditions, we need a theory that blends relativity and quantum mechanics into one. Yet despite decades of effort, no such unified theory has been confirmed. The frontier where this struggle plays out is the Planck scale, named after the physicist Max Planck. At this scale, distances are around 10 to the minus 35 meters, and times are around 10 to the minus 44 seconds. These numbers are so tiny they defy ordinary comprehension. A Planck length is to the size of an atom what an atom is to the size of the solar system. It is the scale at which the smooth fabric of space-time might reveal itself to be something else entirely, granular, foamy, or woven from deeper threads. Physicists sometimes imagine space-time at the Planck scale as a kind of quantum foam, bubbling with fluctuations. At such scales, geometry itself may no longer be continuous. Distances and durations might come in discrete quanta, like the pixels of a cosmic screen. The uncertainty principle would apply not just to particles moving in space-time, but to space-time itself. Trying to measure a position or a moment with Planck-scale precision may only cause space-time to writhe with fluctuations, erasing any certainty. Attempts to bridge the gap have led to bold new frameworks. String theory imagines that particles are not points, but tiny vibrating strings, their harmonies creating the particles we see. In this picture, space-time itself emerges from the interactions of strings. Loop quantum gravity, another approach, suggests that space-time is made of finite loops of geometry, woven into a network at the Planck scale. Both ideas are mathematically rich, but neither has yet found experimental proof. The difficulty is partly practical. The Planck scale is so remote from anything we can probe with current technology that direct experiments are nearly impossible. Particle accelerators like the Large Hadron Collider operate at energies trillions of times smaller than what would be required. Black holes in the early universe may hold the clues, but they are not easy laboratories to work with. For now, physicists are left with thought experiments, mathematical models and indirect hints. Despite the challenges, the tension between relativity and quantum mechanics is also fruitful. It has already led to deep insights, like Hawking's discovery that black holes radiate, an effect that arises precisely because quantum mechanics acts in curved space-time. It has inspired new ideas about information, entropy, and the possibility that space-time itself might be emergent, something that arises from more fundamental quantum connections. What makes this struggle so fascinating is that both theories are unquestionably correct in their own domains. Relativity has been confirmed by every test, from the bending of light in eclipses to the timing of pulsars. Quantum mechanics underpins the entire technological world we live in. And yet, when their territories overlap, they resist being merged. It is as though nature has given us two masterpieces but hidden the key that connects them. The mystery of how quantum physics and spacetime fit together is not just a technical problem. It touches the deepest questions of reality. Is spacetime fundamental, or does it emerge from something deeper? Is the universe continuous or discrete at its core? Can the smooth curves of Einstein's geometry and the jittery quanta of the microscopic world be reconciled into one seamless picture? For now, we do not know. But in that not knowing lies possibility. The conflict between relativity and quantum mechanics is a reminder that even our most brilliant theories are provisional, stepping stones toward a greater understanding. Somewhere at the Planck scale, hidden in the froth of quantum foam, the answer waits. Whether it comes from strings, loops, or something no one has yet imagined, it will reshape our understanding of both the very large and the very small. Until then, we live in a universe where two grand stories run side by side, their harmony still to be written. For most of our lives, space-time feels smooth. We move through it without noticing any gaps, as if it were an unbroken stage stretching endlessly in every direction. We can walk across a room, watch the second-hand sweep across a clock, or trace the arc of the moon, and nothing about these experiences suggests that space-time might be anything other than continuous. Einstein's equations too treat space-time as a perfectly smooth fabric. But the question lingers, is this smoothness real? Or is it an illusion that breaks down when we zoom in far enough? At the Planck scale, around 10 to the minus 35 meters, our best theories stop playing nicely with each other. General relativity insists that space-time is smooth, while quantum mechanics suggests that nothing can be perfectly continuous. If matter and energy come in discrete packets, perhaps space-time does too. Physicists have spent decades developing frameworks that try to answer this question, and the answers they propose are as imaginative as they are daring. One approach is loop quantum gravity. In this picture, space-time is not continuous at all, but made of finite loops of geometry woven into a network. These loops are unimaginably small, far beyond anything we could directly observe, but together they create the illusion of smoothness, much as countless pixels form the seamless image on a screen. Just as you cannot divide an electron into halves or quarters, you cannot divide space-time indefinitely. At its foundation, loop quantum gravity says, the universe is quantized, built of indivisible atoms of space and time. The mathematics of loop quantum gravity produces some striking possibilities. For example, singularities, those infinities predicted at the centers of black holes or at the beginning of the universe, may not exist at all. Instead, space-time's grainy structure could prevent curvature from becoming infinite, replacing singularities with finite bouncing states. The Big Bang might give way to a big bounce, where a previous universe collapsed and rebounded into the one we inhabit now. Black holes might not end in a bottomless pit, but in a region where space-time transitions into another form. These are still speculative ideas, but they show how discreteness might rewrite the story of the cosmos. Another contender is string theory, which offers a radically different perspective. Rather than treating space-time as grainy, string theory suggests it is not fundamental at all. Instead, what we perceive as space-time may emerge from something deeper, tiny, vibrating strings of energy. According to the theory, every particle, the electron, the photon, the quark, is a different vibration mode of a fundamental string. Space and time are not the stage for the strings, but the product of their interactions. In other words, space-time is not the canvas, it is the painting itself, arising from the brushstrokes of the strings. String theory requires extra dimensions, far more than the familiar three of space and one of time. These extra dimensions are curled up so tightly that we cannot see them directly, but they shape the properties of the strings and therefore the physics of our universe. The theory is mathematically rich, offering ways to unify gravity with the other forces. Yet it is also elusive. No experiment has yet confirmed the existence of strings, and some critics argue that the theory risks becoming too detached from testable reality. Still, the idea that space-time itself might be emergent is one of the most intriguing possibilities in modern physics. Perhaps the most mind-bending proposal of all is the holographic principle. Imagine that everything in our three-dimensional universe, including you, me, planets, and galaxies, could be described by information written on a two-dimensional surface at the boundary of space-time. This idea grew from the study of black holes. In the 1970s, Jacob Bekenstein and Stephen Hawking showed that the entropy of a black hole, a measure of its information content, was proportional not to its volume but to the area of its event horizon. It was as though the black hole's secrets were written on its surface rather than hidden inside. Physicists later extended this idea, suggesting that perhaps the entire universe works this way. If so, our reality might be like a hologram, with a full three-dimensional experience emerging from information encoded on a distant surface. This does not mean the world is an illusion. The holographic principle is not saying we are living in a trick of light like a holographic sticker. It is saying that space-time itself might be a projection, a higher dimensional phenomenon emerging from more fundamental information. The holographic view has already provided useful tools for tackling otherwise impossible problems, particularly in understanding quantum gravity and black holes. It may also hint that space-time smoothness is not fundamental but a large-scale effect, like the surface of water appearing smooth even though it is made of jostling molecules. If space-time is built from information, then its apparent continuity may be only a feature of the scale at which we experience it. So, is space-time smooth or grainy? At present, no one knows. Loop quantum gravity points to a discrete fabric woven of finite loops. String theory suggests space-time is not fundamental at all, but an emergent property of deeper vibrations. The holographic principle imagines space-time as the grandest projection in existence, written in code at the universe's edge. Each of these frameworks offers glimpses of an answer, but none has yet been confirmed by experiment. What they share is a recognition that the smoothness we take for granted may not survive the microscope of ultimate physics. The very stage on which reality unfolds may have a deeper structure, whether woven, vibrated, or projected. Space-time, in this view, is not the serene backdrop we once thought, but a dynamic, layered phenomenon, hiding secrets beyond imagination at the smallest scales. Whatever the final answer turns out to be, the question itself pushes us to think differently about the universe. Smooth or grainy, emergent or fundamental, space-time is not simple. It challenges us to see the familiar world, the ticking of a clock, the distance between stars, as part of a much larger mystery. We may live our lives unaware of the loops, strings, or holograms beneath our feet, but they may hold the key to understanding the true nature of reality. Until that key is found, we walk across a stage that feels smooth, even as physics whispers that beneath it lies something far stranger. For most of history, physics has been about matter and energy, about particles and forces. But in recent decades, a surprising idea has taken hold. Perhaps the deepest layer of reality is not made of matter at all, but of information. Space and time themselves, in this view, may be the ultimate expression of information at work. It is a strange thought, but one that has gained traction thanks to black holes, quantum entanglement, and the provocative vision of physicists who dared to ask whether the universe could be described in bits and bytes. The story begins with black holes and what has come to be called the information paradox. In the 1970s, Stephen Hawking discovered that black holes are not completely black. Thanks to quantum effects at the event horizon, they emit a faint glow, now known as Hawking radiation. Over unimaginably long timescales, this radiation would cause black holes to slowly evaporate and eventually disappear. At first, this seemed like a triumph of combining relativity with quantum mechanics, but it came with a troubling implication. When matter falls into a black hole, all the details of its structure appear to be lost. A star, a planet, or even a library's worth of books, all are crushed into the same fate, leaving behind only the black hole's mass, spin, and charge. If the black hole then evaporates into featureless Hawking radiation, what happens to the information about what went in? Quantum mechanics insists that information cannot be destroyed, but relativity seemed to suggest that black holes swallow information whole. This clash became one of the great unsolved puzzles of physics, shaking confidence in our understanding of both gravity and quantum rules. Over time, many physicists began to suspect that the answer lay in a new perspective. Information is never truly lost. Instead, it may be encoded in subtle ways, either in the Hawking radiation itself or on the event horizon of the black hole. The black hole, in this view, acts less like a cosmic shredder and more like a cosmic librarian, storing information in a hidden catalogue. The paradox has not been fully resolved, but it has changed the way physicists think about space-time. If information is preserved even in the most extreme conditions, perhaps information is more fundamental than space, time, or matter. Another clue comes from quantum entanglement, the mysterious connection that allows particles separated by vast distances to share a single quantum state. Einstein famously called it spooky action at distance, because measuring one particle instantly affects the state of the other, no matter how far apart they are. Entanglement has been confirmed repeatedly in experiments, and it underpins modern technologies like quantum computing. But its significance may run deeper still. In the last few decades, some physicists have suggested that entanglement itself may be the glue that holds space-time together. The idea is startling, that the geometry of space, its very connectedness, arises from patterns of quantum information. Imagine entangled particles as threads. Alone, each thread is fragile. Woven together, the threads create a fabric. In this analogy, space-time itself could be a tapestry woven from entanglement. Pull the threads apart and the fabric unravels. This vision has been supported by surprising results in theoretical physics. In certain models, calculations of space-time geometry can be directly translated into calculations of entanglement entropy, a measure of how much information is shared between quantum systems. It is as though the map of space-time and the map of quantum entanglement are two versions of the same thing. Geometry may not be primary at all. Instead, it may emerge from information. This brings us to the bold phrase coined by physicist John Archibald Wheeler, "it from bit." Wheeler was one of the great thinkers of the 20th century, a mentor to many physicists who went on to reshape our understanding of the cosmos. His "it from bit" slogan captured the radical idea that every particle, every field, every piece of the physical world, the it, ultimately arises from information, the bit. Wheeler argued that reality is fundamentally participatory. The universe is not a passive stage, but a system that comes into being through interactions, through the answering of yes or no questions at the quantum level. Each act of measurement, each collapse of a wave function, is a kind of choice, a binary event that adds to the information content of the universe. In this way, the physical world might be nothing more than the accumulation of information woven into patterns that appear as matter, energy, space, and time. If this sounds abstract, consider how deeply information already rules our lives. The device you're listening on is built on the manipulation of bits. Our communications, our data, even our social connections are encoded and transmitted as information. Physics is suggesting that the universe itself may work in much the same way, with space-time as the ultimate information processor. The implications are profound. If space-time is information, then many puzzles in physics might be reframed. the black hole information paradox becomes a problem of bookkeeping, not destruction. Entanglement becomes not a mysterious add-on to physics, but the foundation of geometry itself. The expansion of the universe, the flow of time, the behavior of matter, all may ultimately reduce to patterns of information at play. None of this is proven. Experiments have not yet revealed whether space-time truly emerges from entanglement, or whether Wheeler's "it from bit" is more than a poetic slogan. Yet the convergence of ideas from black holes, quantum mechanics, and information theory has shifted the conversation. Information is no longer seen as a mere description of the universe. It may be the substance of the universe. The beauty of this view is that it unites physics with something universal and familiar. We all live immersed in information. Our thoughts, memories, and histories are made of it. To think that space-time itself might also be built from information is both humbling and inspiring. It suggests that the universe is not just a stage of matter and energy, but a vast evolving web of knowledge, logic, and possibility. Perhaps one day experiments will confirm that space and time are not fundamental but emergent, written in the language of information. Until then, the idea invites us to imagine the cosmos not as a cold expanse of matter but as something closer to a story, bits woven into its fabric, telling the tale of existence itself. When you look up at the night sky, the stars seem scattered almost at random, sprinkled across the blackness like salt on a dark tablecloth. But when astronomers map the universe on the largest scales, a pattern emerges. Galaxies are not scattered haphazardly at all. They gather into clusters, those clusters connect into filaments, and the filaments weave together into a vast web-like structure that stretches across billions of light years. This cosmic web is one of the most striking features of the universe, and at its heart lies the geometry of space-time. To understand how this grand structure arises, we need to remember that galaxies, stars, and planets are not separate from space-time but part of it. When matter clumps under gravity, it does not just pull on itself. It bends the fabric of space-time, deepening wells in which galaxies and clusters can settle. Over cosmic history, these bends have guided the flow of matter like invisible riverbeds, shaping the universe into the web we see today. The story begins with tiny ripples in the density of the early universe. After the Big Bang, space-time expanded rapidly, leaving behind a nearly uniform sea of matter and radiation. But it was not perfectly uniform. Quantum fluctuations at the very beginning, magnified by cosmic inflation, seeded tiny variations, slight differences in density scattered across space-time. These differences were imprinted in the cosmic microwave background, the faint afterglow of the early universe, which we can still observe today. As billions of years passed, gravity amplified those tiny ripples. Denser regions pulled in more matter, growing into knots of galaxies. Less dense regions emptied out, becoming cosmic voids. The result is the vast pattern we call the cosmic web, great filaments stretching like bridges between clusters, with enormous empty regions spanning hundreds of millions of light years. If you could step outside the universe and look down, it would look like a three-dimensional spiderweb, with galaxies as the bright dewdrops strung along its strands. What makes this so remarkable is that the shape of the cosmic web is not arbitrary. It is space-time's fingerprint, a record of how geometry and gravity have worked over cosmic history. The scale and distribution of the filaments match the predictions of Einstein's theory of general relativity, when combined with the observed contents of the universe: ordinary matter, dark matter, and dark energy. The very layout of galaxies across billions of light years is a silent testimony to the nature of space-time. Dark matter, though invisible, plays a starring role in this story. It does not shine or absorb light, but it outweighs ordinary matter by about 5-1. It gathers into massive halos that sculpt space-time, providing the gravitational scaffolding upon which galaxies form. Where the dark matter clumps, space-time curves more deeply, and galaxies fall into those wells. Without dark matter, the cosmic web as we see it could never have taken shape. The luminous structure of the universe is really a shadow cast upon space-time by this unseen substance. On even larger scales, another ingredient comes into play: dark energy. While dark matter pulls structures together, dark energy drives the expansion of space-time itself, pushing galaxies apart. Over billions of years, the tug-of-war between the pull of matter and the push of expansion has frozen some structures into place while stretching others farther apart. The balance between these forces is written into the thickness of the filaments, the emptiness of the voids, and the clustering of galaxies across cosmic distances. Astronomers today map this structure using galaxy surveys, charting millions of galaxies and their positions. The Sloan Digital Sky Survey, for instance, has produced three-dimensional maps that reveal the cosmic web in stunning detail. These maps are not just beautiful, they're scientific gold mines. By studying the patterns of clustering, scientists can test theories of gravity, measure the expansion rate of the universe, and probe the properties of dark matter and dark energy. In effect, the cosmic web acts as a giant laboratory, allowing us to test space-time itself across unimaginable distances. It is humbling to realize that the largest structures in the universe emerge from the same physics that governs falling apples and orbiting moons. Gravity, described by the curvature of space-time, has shaped not just local motions but the architecture of the entire cosmos. From the delicate ripples imprinted in the infant universe to the majestic clusters of galaxies we see today, the story of structure is the story of space-time at work. Even more astonishing is that we are part of this web. The Milky Way itself lies on a filament, connected to clusters and voids like a single bead on a cosmic necklace. Our local region of the web is called the Laniakea supercluster, a sprawling structure containing hundreds of thousands of galaxies bound together by gravity. To us, home is Earth, orbiting the Sun. But on the grandest scales, home is a filament of the cosmic web, one thread in space-time's vast tapestry. The cosmic web also invites a sense of perspective. From our limited vantage point on Earth, the universe can seem random or chaotic. But when we step back, really step back, the order emerges. Space-time is not just a stage, but a sculptor, shaping the grand design of the cosmos. The filaments, voids, and clusters are not accidents, but the natural outcome of space-time's rules. The universe, it turns out, has structure on scales so large that it defies imagination, yet those structures obey the same geometry that governs the orbit of the moon. When we look at the cosmic web, we're seeing space-time revealed in form. The bends of space-time guide matter, and matter in turn deepens those bends. Together, they weave a universe of breathtaking intricacy. Galaxies spin, clusters collide, voids expand, and yet the pattern persists, stretching across billions of light years. The fingerprint of space-time is etched into the cosmos itself, waiting for us to trace its lines and wonder at the hand that drew them. Einstein's equations of general relativity are among the most beautiful pieces of mathematics ever written down. They describe how space-time curves in response to matter and energy, and how that curvature, in turn, directs the motion of matter. But unlike the tidy equations of Newton, Einstein's equations are not limited to one neat solution. They are a set of rules so flexible that they admit an astonishing variety of possible universes, some of which are elegant, others bizarre, and a few that seem downright impossible. These strange, exotic space-times remind us that the laws of physics are generous in what they allow, even if nature is choosier in what it actually builds. One of the most intriguing examples was discovered in 1949 by the logician Kurt Gödel, famous for his incompleteness theorems. Gödel was a close friend of Einstein's at Princeton, and while Einstein was pondering the expansion of the universe, Gödel was playing with the mathematics of relativity. What he found was astonishing. A rotating universe, one in which the entire fabric of space-time swirled like a cosmic whirlpool. Gödel's universe had a disturbing property. In it, You could draw paths through space-time that looped back on themselves, so that by travelling far enough you could return not just to where you started, but to when you started. These closed time-like curves would allow time travel to the past, at least mathematically. The idea fascinated Einstein, but also troubled him. He had shown that space-time could bend, stretch, and ripple, but Gödel showed it could also twist in ways that undermined the very idea of causality. If time loops were possible, what would stop paradoxes? Effects arriving before their causes, people meeting their younger selves, or events erasing their own origins? Gödel's solution was a perfectly valid answer to Einstein's equations, but most physicists suspect that our universe is not rotating in that way. Observations show no evidence of the global rotation his model requires. Still, Gödel's work was a revelation, showing that relativity allowed far stranger possibilities than even Einstein had anticipated. Other exotic spacetimes arise from considering different kinds of curvature on the larger scales. One of the simplest is called de Sitter spacetime, discovered in 1917 by Willem de Sitter. It is a solution to Einstein's equations with a positive cosmological constant, meaning it describes a universe dominated by a repulsive energy that drives expansion. Sound familiar? Modern cosmology tells us that our universe is indeed expanding at an accelerating rate, driven by dark energy, which behaves much like de Sitter's cosmological constant. In a sense, our cosmos today resembles de Sitter spacetime on vast scales. At the opposite extreme lies anti-de Sitter spacetime, which curves inward rather than outward. Imagine spacetime shaped not like an inflating balloon, but like a saddle, its geometry warped so that parallel lines tend to converge. Anti-de Sitter spacetime does not describe our universe, but it has become a playground for theoretical physics. It forms the foundation of the famous ADS/CFT correspondence, a conjecture that links gravity and anti-de Sitter spacetime to a quantum field theory defined on its boundary. This strange duality has given physicists one of the most powerful tools yet for exploring the relationship between spacetime and quantum mechanics. These exotic solutions remind us of a crucial truth. Einstein's equations are like a recipe book with many possible dishes. Some are familiar, like the flat spacetime of special relativity, or the gently curved space-time of a star's gravity. Others are wild experiments in geometry, rotating universes, inflating voids, saddle-shaped infinities. The equations do not forbid them. The real universe simply chooses not to serve them up. But why not? If relativity allows closed time loops, why don't we see them? If exotic geometries exist in theory, why isn't our cosmos built from them? The answer lies in the distinction between mathematical solutions and physical reality. Einstein's equations are broad, but they are not the whole story. They must be supplemented by conditions from the real world, the actual distribution of matter, the quantum nature of fields, and the demand that physics remain consistent. Gödel's universe is mathematically possible, but the matter distribution it requires does not match what we observe. Anti-de Sitter space is mathematically rich, but it does not fit the accelerating expansion revealed by our telescopes. Sometimes, exotic spacetimes may even serve as warnings. Closed time loops are possible in theory, but many physicists believe there is a chronology protection mechanism in the universe that prevents them from becoming real. Exotic matter might keep wormholes open in equations, but the actual laws of physics may forbid the quantities needed. In this way, Einstein's equations tempt us with strange visions, but nature seems to prefer stability over paradox. Still, these solutions are invaluable. They stretch our imaginations and our mathematics. They test the limits of what relativity can describe. They provide laboratories for exploring the edges of physics, even if the real universe does not look like them. Exotic spacetimes show us that the cosmos could have been different, that our reality is one among many possible geometries allowed by the deep rules of relativity. In the end, these bizarre models remind us that space-time is not a simple stage. It is a flexible, dynamic fabric capable of taking forms far beyond our daily experience. Our universe may have chosen one particular path, but the mathematics tells us of countless others, each with its own strange beauty. Some twist time into loops, others stretch space into saddles, and still others inflate endlessly. They are the ghosts of possible universes, whispering from the equations reminders that reality is stranger and more varied than we often dare to think. When we talk about the universe, we often picture it as an endless stretch of stars and galaxies going on forever in every direction. But one of the most profound questions in cosmology is deceptively simple. What is the shape of the universe? This is not a matter of whether it is round or square, but of how space-time itself is curved and connected. The answer could determine whether the cosmos extends without limit, loops back on itself, or hides topological twists we have barely begun to imagine. To begin, imagine space as a giant sheet. That sheet can be curved in different ways. If the universe is flat, the geometry of space-time follows the familiar rules of Euclidean geometry, the kind we learn in school. Parallel lines never meet. Triangles add up to 180 degrees, and space stretches infinitely in all directions. A flat universe would go on forever, with no boundary and no edge, just an endless expanse of galaxies. If the universe is closed, its geometry is curved like the surface of a sphere. In such a cosmos, parallel lines eventually meet, and triangles add up to more than 180 degrees. If you travel far enough in a straight line, you might eventually return to your starting point, just as a sailor circumnavigating the Earth comes back to port. A closed universe is finite in volume, but it has no edge. There is no wall at the end of space, just a continuous loop that brings you home again. Then there is the open universe, curved like a saddle. Here, parallel lines diverge, and triangles add up to less than 180 degrees. Space stretches outward infinitely, but with a negative curvature that shapes the overall geometry of the cosmos. An open universe would expand forever, its galaxies rushing apart endlessly, with no chance of ever circling back together. Astronomers have spent decades trying to measure which of these shapes matches reality. The key lies in the cosmic microwave background, the faint afterglow of the Big Bang. By studying the patterns of hot and cold spots in this ancient light, scientists can measure the curvature of the universe with exquisite precision. So far, the results suggest that the universe is astonishingly close to flat. If it has curvature at all, it is so slight that it would take more than 100 billion light-years to notice the difference. But curvature is only part of the story. There is also the question of topology, the way space might be connected to itself. Topology is less about local curvature and more about global shape. To see the difference, think of a video game world where walking off the edge of the screen on the right brings you back on the left. Locally, everything looks flat, but globally the space is connected in a loop. Could the universe itself be like this? A kind of cosmic video game where travelling far enough in one direction eventually brings you back from the other side. Some cosmologists have seriously considered this possibility. A universe with such a wraparound topology could be finite yet unbounded, like the surface of a torus or donut. Light travelling through such a cosmos might wrap around multiple times, producing repeating patterns in the cosmic microwave background. Researchers have searched for these repetitions, for pairs of identical circles imprinted in the sky. So far, no clear evidence has been found, but the idea remains tantalizing. If the universe does have a wraparound shape, it would redefine our sense of scale. What we think of as billions of galaxies might actually be multiple images of the same galaxies, seen along different paths of light. The cosmos could be smaller and more interconnected than we imagine, with space-time folding back on itself in ways we cannot yet detect. Even in a flat universe, topology could still play a role. A flat sheet can be connected into a cylinder or torus, just as a piece of paper can be rolled or glued in different ways. Likewise, Spacetime may be globally connected in shapes that are difficult to visualize. It might not be infinite at all, but instead finite and multiply connected, with strange roots that link faraway regions. These questions are not idle speculation. They cut to the heart of how the cosmos began and how it may end. A closed universe could one day halt its expansion and collapse back into a big crunch. An open or flat universe may expand forever, with galaxies drifting apart until they are lost beyond the cosmic horizon. Topology, too, could affect cosmic evolution, influencing how matter clumped and how light travelled in the early universe. The mystery of the universe's shape also challenges our imagination. We're used to thinking in terms of familiar three-dimensional objects, spheres, saddles, donuts. But spacetime may not fit neatly into any analogy. Its true shape may be more complex than anything we can picture, describable only through mathematics. And yet, through observations of the cosmic microwave background, galaxy surveys and gravitational lensing, we're beginning to tease out hints of that shape, sketching the outline of the stage upon which all cosmic drama unfolds. Whether the universe is flat, closed or open, whether it stretches infinitely or loops back on itself, the very act of asking reveals something profound. We live inside space-time, woven into its fabric, and yet we can step back through science and imagination and ask about its global nature. It is like being characters in a story who suddenly wonder about the binding of the book, the paper on which the tale is written. At present, the evidence points to a universe that is flat and vast beyond comprehension, perhaps infinite. But the possibility of hidden curvature or exotic topology remains open. The cosmos may yet surprise us with twists that connect its farthest reaches or folds that reveal it is smaller than it appears. Until we know for certain, the shape of the universe remains one of the grandest questions of all. Is space endless, or does it curve back on itself? Is the cosmic stage flat and infinite, or wrapped in ways we have barely begun to imagine? Whatever the answer, it is space-time itself that holds the key, shaping not just where we are, but what it means for there to be a where at all. Space-time might sound like a lofty concept, something reserved for physicists scribbling on chalkboards or astronomers peering through massive telescopes. Yet it is not just an abstract framework for the cosmos. It quietly shapes the details of our everyday lives, from the way your phone finds directions to how astronauts experience time differently in orbit. Space-time is not some distant concept, but the invisible geometry we're all living in. Take clocks, for instance. We tend to think of them as impartial referees of time, ticking along in perfect rhythm. But relativity teaches us that clocks are not impartial at all. Their ticking depends on how they move and where they are in a gravitational field. A clock sitting on the ground on Earth runs at a slightly different rate than one perched on top of a mountain. The difference is tiny, measured in billionths of a second, but it is real. Time itself flows at different speeds depending on how space-time is curved by gravity. Nowhere is this clearer than in the satellites orbiting above us. The global positioning system relies on a constellation of satellites, each carrying an atomic clock so precise it could keep time to within a billionth of a second. To triangulate your position, your phone listens to signals from several satellites and measures the difference in arrival times. But here's the twist. Without relativity, GPS would not work. Those satellites are moving quickly relative to Earth's surface, and according to special relativity, moving clocks tick more slowly. At the same time, the satellites are farther from Earth's mass, so gravity curves space-time less strongly where they are. That means their clocks tick faster according to general relativity. The two effects do not cancel, they combine. Net result, the clocks in orbit tick about 38 microseconds faster every day than those on Earth. If this were not corrected, your phone's location would drift by kilometers within hours. In other words, every time you check for the nearest cafe, you're relying on Einstein's insights about space-time. Your phone is, in a sense, a relativity device. Astronauts experience space-time's effects more directly. Consider those aboard the International Space Station. They orbit Earth at about 28,000 kilometers per hour, and this high speed slows their clocks relative to ours on the ground. At the same time, because they are farther from Earth's gravitational pull, their clocks tick faster. The balance of the two effects means that astronauts age very slightly more slowly than those of us left behind. After 6 months in orbit, the difference amounts to just milliseconds, but it is measurable. This twin paradox effect, once a thought experiment, is now a routine feature of space travel. For astronauts venturing deeper into space, the differences grow larger. Near massive bodies like black holes, time dilation becomes extreme. A clock ticking near the event horizon of a black hole would appear to almost stop compared to one far away. While we do not yet send people to such extremes, the principle reminds us that our experience of time is not universal. It is local, bound to our particular path through space-time. The practical side of cosmic geometry shows up in other surprising ways. Engineers designing particle accelerators must account for relativistic effects. Particles racing near the speed of light live longer in the lab than they would at rest, thanks to time dilation. Astronomers measuring the signals from pulsars, rapidly rotating neutron stars, must include relativistic corrections to match the timing of their radio pulses. Even mundane technologies like telecommunications and banking rely on synchronized clocks that must factor in the geometry of space-time. What makes all this so striking is that space-time is not an exotic add-on to physics. It is the stage we are always inhabiting. We do not feel Earth's curvature beneath our feet, but it shapes the horizon. We do not notice the slowing of time at sea level compared to the mountains, but it is written into the equations that govern our world. Space-time is not just the fabric of the cosmos, but the invisible infrastructure of our daily existence. Living in space-time also shapes how we imagine the future of exploration. When we think about interstellar travel, the real challenge is not just distance, but time. Even at a fraction of the speed of light, journeys to nearby stars would take decades or centuries. Time dilation could make such voyages stranger still. Travellers moving close to light speed might experience only a few years while centuries pass on Earth. The geometry of space-time thus defines not only what is possible, but what is meaningful in terms of connection, communication, and exploration. There is also a philosophical side to living in space-time. We tend to think of ourselves as beings in time, moving through it as it flows. Relativity shows that we are beings of space-time, tracing world lines through a four-dimensional fabric. Each heartbeat, each step, each thought is a point along that path. The physics may be abstract, but the experience is as personal as life itself. And perhaps the most humbling realization is that we are not separate from the cosmic geometry. We are participants in it. Every mass bends space-time, and that includes you. Your body warps the geometry around it, however imperceptibly. When you move, you carve a path through space-time that is uniquely yours, a world line no one else can trace. The same rules that govern galaxies and black holes are at work in the seconds you live and the meters you walk, so while space-time may seem like the province of theorists and astronomers, it is in fact the medium of our daily lives. It keeps your phone honest, it makes astronauts younger than their twins, and it ensures that every moment you experience is part of a grand geometry that stretches across the universe. Living in space-time is not something we choose, it is the condition of existence itself, and once you notice it, the ordinary becomes extraordinary. The tick of a clock, the ping of a GPS signal, the arc of a satellite, all gentle reminders that we are walking not on a flat world, but on the fabric of the cosmos. When Einstein stitched space and time together into a single fabric, it solved many puzzles of physics. Planets curved around stars, light bent across the sky, and the expansion of the cosmos itself could be described with elegance. But in solving those problems, Einstein raised one that may never go away. What is space-time really? Is it a thing in its own right, or is it simply a web of relationships between objects? Does time truly flow, or is that just the way our minds perceive it? At the boundary of physics and philosophy, space-time becomes as much a riddle as a framework. The first way of seeing space-time is to treat it as a substance, a real entity that exists independently of the matter within it. In this view, space-time is like the canvas on which the universe is painted. Stars, planets, and particles are daubs of paint, but the canvas itself has texture and presence. Einstein's equations seem to support this idea because they describe how space-time bends, stretches, and ripples. A substance can be dynamic, and space-time certainly is. It is not empty nothingness, but something that responds to mass and energy, shaping and being shaped in turn. Yet some philosophers and physicists argue that this picture may be misleading. They prefer a relational view, that space-time is not a thing, but simply the sum of relationships between objects and events. In this vision, what exists are particles, fields, and interactions. Space-time is only the language we use to describe the distances, durations, and connections among them. Remove the matter, and there is no leftover stage, no fabric without the threads. To call space-time a substance, they argue, is to mistake the map for the territory. This debate is not new. Newton imagined space and time as absolute, existing independently whether or not anything was in them. Leibniz, his philosophical rival, saw them as relational, emerging from the web of connections among objects. Einstein's work gave new fuel to both sides. The dynamism of space-time seems to favour the substance view, but the relativity of simultaneity, where different observers disagree about what is happening now, suggests that space-time is a relational structure, defined differently for each participant. Then there is the question of time itself. We experience it as flowing, carrying us from past to present to future. But in the block universe picture, all moments exist equally, laid out in the four-dimensional fabric of space-time. Yesterday, today, and tomorrow are simply coordinates on the map, no more privileged than north or south. In this view, time does not flow. It is our consciousness that moves, giving the illusion of passage. Is that illusion or reality? Physics does not give a definitive answer. The equations of relativity work equally well forward or backward in time. There is no fundamental arrow written into the math. The arrow we observe seems to come instead from entropy, the tendency of systems to move from order to disorder. Eggs break, but they do not unbreak. Tea cools, but it does not reheat itself. This thermodynamic arrow gives time its one-way feel, but it may be a feature of statistics rather than an absolute law. The universe may be timeless at its core, with flow emerging only from the way large-scale systems behave. This clash between our inner experience and the outer description of physics has long invited metaphysical speculation. Augustine, writing more than 1500 years ago, admitted that he knew what time was until someone asked him to explain it. Philosophers since have wrestled with whether time is an objective feature of reality or a projection of the human mind. Modern physics has sharpened the question rather than solved it. If time is an illusion, it is the most persistent one we know. Even within physics, the ontological status of space-time is unsettled. In quantum mechanics, fields ripple and particles flicker, but they do so against the backdrop of space-time. In quantum gravity, however, space-time itself may dissolve into something more fundamental, loops, strings, or networks of information. If space-time is emergent, then it is neither substance nor relation in the ordinary sense. It would be more like a pattern, an approximate description that arises from deeper structures we have not yet fully understood. John Archibald Wheeler's famous phrase, "it from bit," captures this radical possibility. If space-time itself arises from information, then the debate between substance and relation may dissolve. Space-time would not be a thing, nor merely the connections between things, but the expression of information at work. Entanglement, in particular, has been proposed as the very thread from which space-time is woven. In that case, Spacetime might be closer to a story than to a stage, a narrative of relationships encoded in quantum bits. At the boundary of physics and philosophy, these questions blur. Is spacetime real in itself? Does time flow or only appear to? Are our most fundamental concepts emergent rather than absolute? No experiment has yet settled these matters, and perhaps none ever will. Yet the act of asking shapes the way we think about the universe. Spacetime is not just an arena for physics, but a mirror for human thought, reflecting back our deepest intuitions and challenging us to see beyond them. For daily life, of course, none of this ambiguity matters. Your watch ticks, your GPS works, and the sun will rise tomorrow. But when we step back and ask what those ticks, coordinates and risings mean, we find ourselves at the edge of understanding. Space-time is both the most concrete of realities, we cannot step outside it, and the most elusive, because we cannot pin down what it really is. It is stage, relation, pattern, and perhaps even illusion all at once. Perhaps the ultimate lesson is that space-time is not a thing to be pinned down at all, but a way of seeing. It is the language in which the universe speaks to itself, the grammar of existence. Whether substance, relation, or something else entirely, it remains the framework that lets us ask the question in the first place. And in that sense, space-time is as real as it needs to be, the very fabric of reality and the deepest mystery woven through it. The story of space-time is not finished. In fact, it may only just be beginning. Einstein gave us the framework more than a century ago, and since then we have tested it in eclipses, in GPS satellites, and in the collisions of black holes. Each time the theory has held strong, yet for all its successes, general relativity is incomplete. It does not sit comfortably with quantum mechanics, and it leaves open questions about the earliest moments of the universe and the deepest interiors of black holes. The next century of physics may be defined by the attempt to go further, to probe space-time more deeply, and to discover whether it is fundamental or something that emerges from hidden rules. One of the most exciting frontiers is gravitational wave astronomy. In 2015, LIGO detected the first ripples in space-time from two black holes colliding more than 1 billion light-years away. That breakthrough was just the overture. The detectors have since been joined by Virgo in Italy and Kaigura in Japan, and already dozens of events have been recorded. Yet these observatories are only the first generation. Plans are underway for far more sensitive detectors that will transform gravitational wave science from a novelty into a standard tool of astronomy. On Earth, projects like the Einstein Telescope in Europe and the Cosmic Explorer in the United States aim to build interferometers with arms 10 times longer than LIGO's. These instruments would be sensitive enough to hear black hole collisions from the dawn of galaxy formation, and perhaps even the whispers of primordial waves from the early universe. In space, the Laser Interferometer Space Antenna, better known as LISAA, is scheduled to launch in the 2030s. With the arms millions of kilometers long, LISA will be able to detect the deep bass notes of the gravitational wave symphony, mergers of supermassive black holes, and possibly even signals from exotic sources such as cosmic strings. Each of these projects promises to open new windows on space-time, letting us not only see the universe, but also listen to its geometry in action. At the same time, physicists are pushing toward experiments that test quantum gravity. For decades, the Planck scale, the unimaginably tiny realm where quantum mechanics and relativity collide, has been thought beyond our reach. But clever ideas are emerging. Tabletop experiments are being designed to test whether gravity can produce quantum entanglement between small objects, a direct probe of whether space-time itself obeys quantum rules. Particle physicists are searching for subtle deviations from Einstein's predictions in the orbits of pulsars and in the way particles interact at high energies. Even precision measurements of atomic clocks, now accurate to better than 1 part in 10 to the 18th, may reveal tiny ripples in space-time or the fingerprints of new physics. Alongside experiments, bold new theories are reshaping how we think about space-time. One possibility that has gained traction is that space-time itself is emergent. In this picture, space and time are not fundamental building blocks, but large-scale effects, much like temperature emerges from the motion of countless atoms. Entanglement may be the true scaffolding, with geometry arising from patterns of quantum information. The holographic principle, string theory, and loop quantum gravity each offer variations on this theme. If correct, then asking, what is space-time, may be like asking, what is a rainbow? It is real, but only as a phenomenon arising from deeper laws. These ideas may sound abstract, but they matter deeply. If space-time is emergent, then black hole singularities, the Big Bang, and other paradoxes may dissolve once we find the underlying structure. The infinities that plague relativity at extreme scales may be artifacts of treating space-time as fundamental when it is not. Understanding its emergence could be the key to unifying physics and explaining why the universe looks the way it does. And yet, for all the progress, vast open questions remain. What exactly happened in the first fraction of a second after the Big Bang? Did space-time begin abruptly? Or did it emerge gradually from a pre-space-time quantum state? What is the true nature of dark energy, the mysterious driver of cosmic acceleration? Is it a property of space-time itself, or a sign of new fields and forces we have yet to discover? Can black holes really destroy information, or will a complete theory show how it is preserved? And most of all, is space-time continuous? Or does it break down into discrete quanta at the Planck scale? These questions are not idle speculation. They cut to the core of what physics is meant to do, describe reality at its most fundamental. Space-time is the canvas on which the universe is painted, but we do not yet know whether that canvas is woven of threads, made of pixels, or projected from elsewhere entirely. Each experiment, each detection, each observation sharpens the picture. With gravitational wave astronomy, quantum gravity tests, and theoretical breakthroughs, we may soon glimpse the true nature of the stage upon which existence unfolds. What makes the future of space-time studies so thrilling is that we are guaranteed surprises. Einstein himself never anticipated gravitational waves being measured or black holes being imaged. The pioneers of quantum theory never dreamed their work might one day suggest that space-time is not fundamental. If the past century of physics has taught us anything, it is that the universe is far stranger than we expect, and each new tool reveals wonders we could not have imagined. So as we look ahead, the study of space-time promises not only answers, but also deeper mysteries. We may discover ripples from the birth of the universe, signs of quantum entanglement woven into geometry, or entirely new principles that rewrite our understanding. Whatever lies ahead, one thing is clear. Space-time, the fabric that underpins everything, still holds secrets waiting to be unraveled. The next chapters in this story are unwritten, and they may change not only how we see the cosmos, but what we believe reality itself to be. From the earliest philosophers gazing at the sky to the physicists writing equations on blackboards, humans have wrestled with the same question. What is space and what is time? For Aristotle, space was a place, the stage where matter resided. For Newton, it was an infinite arena, a backdrop against which the universe played out. For Einstein, the picture changed forever. Space and time fused into space-time, a dynamic fabric capable of bending, rippling, and expanding. Since then, every generation has added new layers, mathematical, experimental, and philosophical. Yet the central mystery remains. We live inside space-time, but we do not yet know what space-time truly is. The history of this idea is itself a journey through human imagination. In the 17th century, Newton described space and time as absolute, the ultimate reference frame. A century later, Leibniz argued that they were not things at all, but simply relations between objects. The argument seemed philosophical then, but Einstein's relativity gave it physical weight. With special relativity, the speed of light became a cosmic anchor, forcing space and time to stretch and contract depending on one's motion. With general relativity, space-time became dynamic, shaped by the presence of mass and energy. The rigid stage of Newton gave way to a living fabric, and the universe itself became an active participant in its own unfolding. This vision was not merely theoretical. Experiments soon confirmed it. Eddington's eclipse expedition in 1919 showed starlight bending around the sun, a direct glimpse of curved space-time. Gravitational lensing revealed galaxies acting as natural telescopes, magnifying objects behind them. The expansion of the universe, first charted by Hubble, showed space-time itself stretching, carrying galaxies with it like raisins in rising dough. Gravitational waves, first detected in 2015, confirm that space-time can ripple like a drum, broadcasting the echoes of black hole collisions across billions of light-years. And perhaps most humbling of all, our phones depend on relativity to function, their GPS receivers correcting for the way clocks tick differently in orbit and on Earth. Space-time is not just the stuff of chalkboards and observatories, it is in your pocket, guiding you to the nearest cafe. Yet even as relativity has triumphed, its partnership with quantum mechanics has been uneasy. Quantum theory paints a world of uncertainty and probability, of particles flickering in and out of existence, of entanglement binding objects across vast distances. Relativity paints a world of smooth geometry, where space-time curves and objects trace continuous paths. Each theory works beautifully in its own domain, yet when brought together, near singularities, at the birth of the universe or at the Planck scale, they clash. Infinities appear, equations break down, and the two great pillars of modern physics seem unwilling to share the same foundation. Out of this tension have grown bold new visions. Loop quantum gravity suggests space-time is grainy, woven from finite loops, a kind of quantum lattice at unimaginably small scales. String theory imagines particles as tiny vibrating strings, with space-time itself emerging from their harmonies. The holographic principle suggests that our three-dimensional universe may be a projection, like a grand cosmic hologram encoded on a distant surface. Each of these ideas hints that space-time may not be fundamental but emergent, a phenomenon arising from something deeper, like temperature emerging from molecular motion. If so, then the true nature of reality may lie not in geometry but in information. Black holes sharpen this perspective. Their event horizons and Hawking radiation force us to confront whether information is lost or preserved, and whether the fabric of space-time itself is woven from quantum bits. Entanglement, once seen as a puzzling curiosity, may be the very glue of space-time. John Archibald Wheeler's phrase, "it from bit," captures this shift. Perhaps all the its of the universe, particles, fields, even space-time itself, arise from the information that underlies them. Amid these scientific advances, the philosophical questions remain as sharp as ever. Is space-time a substance in its own right, bending and rippling like a cosmic fabric? Or is it nothing more than the web of relations between events? Does time truly flow, or is the flow only a feature of consciousness, tracing its path through a block universe where past, present and future coexist? Physics offers equations, but it does not settle the metaphysics. It tells us how space-time behaves, but not what it ultimately is. What makes the study of space-time so captivating is that it's both universal and personal. It shapes galaxies, clusters, and the cosmic web stretching across billions of light-years. It also shapes our daily lives, from the way our phones guide us through traffic to the way astronauts age slightly differently in orbit. It holds the secrets of black holes, wormholes, and horizons we cannot cross. It is the container of our memories and the canvas of our hopes. We cannot step outside space-time to see it whole, yet it is the medium of everything we know, and everything we are. Looking to the future, the questions grow even more profound. Next-generation gravitational wave detectors will listen to the universe with new sensitivity, perhaps catching whispers from the first moments after the Big Bang. Quantum experiments may test whether space-time itself is subject to entanglement and superposition. Theoretical breakthroughs may show us whether space-time is continuous or discrete, fundamental or emergent. Each discovery may answer old questions, but also open new ones. The frontier of space-time is not a boundary we will cross once and be done, but a horizon that recedes as we approach, always offering deeper mysteries. And so, after tracing its history from Aristotle's places to Einstein's curves, after listening to its ripples and pondering its paradoxes, we end with a paradox of our own. Space-time is the most familiar thing of all. It is the backdrop of every breath and heartbeat, and yet it remains the most mysterious. We move within it, shaped by it, sustained by it, but we do not yet know what it is. Perhaps that is the essence of wonder, to live inside a mystery surrounded by it, unable to escape it, and yet able to glimpse its outlines in thought and experiment. As you drift towards sleep tonight, consider this. You are lying not just on a bed, not just under a roof or beneath the stars, but within the very fabric of space-time. Every tick of the clock beside you, every whisper of distant galaxies, every memory and dream, all unfold inside this fabric. It carries you, it shapes you, and it holds you gently, even as it hides its deepest secrets. May that thought bring you peace, that you are woven into the same fabric as the stars, resting within space-time itself, the quietest and most profound of mysteries.